We are going to design a column having uh, vertical load and a heavy bending moment. These things are given here. Design of isolated footing with a column having heavy bending moment. The axial load in the column is 150 kilonewton. For the design aspect, we are assuming these things. The bending moment in x direction is 200 kilonewton meter. The column size is 300 mm by 400 mm, that is zero point 0.3 by zero point 0.4 size of the column. And we are going to use M20 concrete and Fe500 steel we are going to use. Cell bearing capacity of the soil we are assuming is 12 tons per square meter, which is 120 kilonewton per m square. These are the given items. The moment in YY direction we are assuming it as 0 because this is a column having a bending moment in one direction only. We shall see the column cross section drawings. This vertical line is the column. This horizontal is the column footing slab. The Fu is the vertical load. The Mu is the moment. If this moment is applied like this will give a turning to the right side, and so the stress will develop on right side at a higher level. It's going towards the center, the stress will go on reducing in a triangular way. So by here, if we shift the column from this place to somewhere to the left, this load bearing triangle area will be higher. So for that we are shifting the column to the left side, that is to the left side of in the same direction of the moment. So this portion, right side portion is called toe side, left side portion is called heel side. This is the pattern of upward soil pressure because of the moment in the soil area. Because of this vertical load, this is a constant soil pressure in the bottom of the footing slab. These are the measurements we are seeing. This is blue line is the column, the red color is the footing slab. Now we are going to assume that the distance of the slab end to the column face, we are calling it as L face in the toe side. Similarly, the L face in the heel side. If the measurement is taken from center of the column to footing slab end, then it is called L center toe side, L center heel side. Required area for footing is nothing but the load by say bearing capacity. This is load by say bearing capacity. This one is load means the 150 kilonewton by say bearing capacity is 12. This divided by this is this much. This calculation has been done by the Excel by itself. So this is the area required for the footing. Add 5%. For example, it is added which for any deviation add 5%. This total area required is this much. How to find the breadth and depth? Take a root on this. The root is 1.31, square root is 1.145 meter. You take it as breadth is taken as 1.15. So length as per the loading condition, this length must also be 1.15. But there is another parameter acting on the column, which is the moment, which is 200 kilonewton meter. For that, what we are going to do, find the eccentricity. Find how to find the eccentricity. Eccentricity can be this much only. Moment 200 divided by load 150 is 1.33. This is the eccentricity. There is a thumb rule. This thumb rule I have calculated in this way by doing some more calculation on trial and basis. For that we are assuming that the length of footing In moment application direction is taken as 2 times the eccentricity plus L load. L load means the theoretical length for the direct load is the may be taken as the length of the actual footing for the application of load and moment. This is 3.18 meter. So now, as per the including that thumb rule, the total net breadth is 1.15, length is 3.816. Then place the column. The column is to be placed at some eccentricity. See here, the column is at center. The column is at center. This is shifted to some extent. That extent is calculated in this way. E by 2. E by 2. Already we have calculated the measurement eccentricity is 1.33 by 2 is taken as the actual shifting distance. That is 1.33 by 2 is 0.6 measurement by which the column is shifted. Shifted means it means that we are providing the floor footing by moving to the right side. Okay. Some measurements we are going to make the toe side cantilever, reverse cantilever from the column center. L face, L center and etc. we are going to calculate this way. The L face, L center, this we have calculated this much, these things. By seeing the sketch, you can calculate these things. L center in the toe side, L center and L face in the heel side calculated. Similarly, breadth side also we can calculate these things. So these are the 6 values we are calculating before commencing. These dimensions we are calculating and putting it here. Now factored load. The load is given as 150, that is in multiplied by 1.5, then it gives the factored load is 225 kilonewton. Similarly, factored moment is 300. Then the safe bearing capacity is given. This can be maximum up to safe bearing capacity into 1.5. This is 1800 kilonewton per square meter. Now you calculate this soil upward pressure due to load. For the present scenario, present sizes of the footing we are calculating. That is total vertical load divided by the area footing is this much. This calculation has been done by the computer in Excel. Soil upward pressure due to moment. Now we are going to soil upward pressure due to moment means that the triangular portion. See how this triangle, how much will be this triangular measurement we are going to find. Moment equal to total upward soil pressure due to moment into distance of centroid of soil pressure. Centroid of soil pressure means, see here this black line, the upward soil, the center part, this is 2 by 3 of the total length. This span means the cantilever, it's called like this. So mu equal to breadth into upward soil pressure into centroidal distance. This is calculated in this way. See this drawing is the top view of the isolated footing and the column. This shaded portion is the column and the larger portion is the footing slab. As per the design procedure, the shear capacity has to be checked at a distance of D from the column face on left side and right side. The right side, this is the toe side. This will in this side only the higher pressures including the soil pressure for moment is existing. So checking the right side shear at D distance from the face itself is enough. So finding this shear, we shall go to this drawing. This portion is the exterior portion from beyond the distance of D from the column face. So out of the total of the pressure applied over this shaded portion is the shear force going to act on this section. Upward soil pressure due to moment happens in this way. The end soil pressure is QMM, that is moment maximum. Then the soil pressure at a distance of D from the column face is to be calculated for finding this upward soil pressure. QMM, the pressure maximum. This L center, we have already seen that. Center of the column to end of the beam, end of the slab. Then A is the longer side of the column, B is the width of the column, D depth of slab, QD pressure at a distance of D from the column face. QD is equal to QM by Q length into A by B into D. This is as per the drawing. This QM varies from QM to 0. This for interpolation, the QD will be this only. This interpolate it, and this drawing is this formula you will find. Then pressure, how the pressure is to be calculated. The pressure is calculated in two ways. One is the moment, pressure due to moment. This QD we have already calculated, QD plus QM, this breadth into this breadth. This is the distance from this point to this point, then this LD, this is the area of this area, this portion, into what is the average pressure. What is the average pressure? This is average pressure. QD is the pressure at the D distance, QM is the maximum pressure at the last end, by 2 gives the average into the area is the upward pressure due to moment. Similarly, for upper portion, this for load also, B into depth, DL, the area portion, Q load, this is a constant load, so this area is, by adding these two we are finding the upward soil force acting at this section. This is the shearing area at a distance of D is equal to nothing but the breadth into depth is the shearing area, that is the area in which the shear is going to happen, that is this much. Same thing multiplied by S means the shear resisting capacity at the distance of D. Then using the formula as we saw in that image, we are finding the upward soil force exerted on the critical section is this much, 260.11 kilonewton. This is the soil force exerted on the section. The shear bearing capacity is 258, which is less by 2 kilonewton. This is very less, so no problem, we can take it. Next check is checking the same shear at a distance of D by 2, but all round the column face. This checking is also called the punching shear force. See, this is the another explaining image or drawing. This is two-way shear, checking or punching shear. A and B are the column sizes. Shearing area. Now the shearing area is this. The sheared portion is column. This outer line is the footing outer line. This smaller line at some distance from the column face is the critical section at which the shear is to be checked. That critical section is taken as at a distance of D by 2 from the column face in length in the A side and B side. So the pressure, the total soil upward force in the sheared area is to be calculated. This calculation is done in 3 types. One, firstly, the right side, toe side beyond this critical section is calculated. Then width side, the top side and bottom side is calculated. Then the left side. The shear force exerted by this sheared area over that all round critical section is calculated. Here, as done in the previous section, we calculated the Q at D distance. We calculated. Here we are calculating at the shear at d by 2 distance. This is nothing but this linear interpolation qm by length into a by 2 plus d by 2. A by 2 means the column width, column longer side by 2 plus d by 2 is the distance. So this is q d by 2. So upward pressure exerted by this area over this section is calculated in this formula. See, B is calculated, the total B, then area L face minus d by 2. This is length for L d by 2 into Q load. Q load is pressure due to vertical load only, plus this triangular, this is a varying load, varying pressure due to moment. B into the same thing, L face minus d by 2 into the pressure, this total area, Q d by 2 plus Q mm by 2. This plus this by 2 is the average into this area. This one is this adding these together is the pressure exerted by this portion, upward soil pressure over this section. Similarly for width portion, there will be only for the full portion a static, that is vertical load upward pressure will be there. For the 50% of the portion, right side, for 50% the varying load will be there, varying earth upward pressure will be there. This is calculated, this formula, these things you check it by yourself and this will be okay. Similarly on the left side, for the heel side also, this is the formula I have arrived. You can, on seeing this thing deeply, you can arrive these formulas are correct. Okay, checking the shear in two way, that is punching shear checking. These are the formulas we saw in the photos, images we saw just before. The q by 2 at d by 2 distance is this one. Then the upward soil pressure beyond d by 2 distance on toe side, following the formula, this is the value we have arrived. Then the upside pressure beyond d by 2 distance in the breadth side. Applying the same formula we arrived in the previous image, this one. In the heel side, using the same type of formula, this is so adding all these things, this is the total shear force exerted over that d by 2 distance all round critical section. This shear force exerted on the section is 320 kilonewton, whereas the shear capacity of the section is 1400 something kilonewton. This exerted shear is very less than the shear capacity of the section. Then so the section we proposed is well safe. Checking the bending moment at the column face. At that area we should arrive the bending moment and we should arrive the reinforcement at the column face. Column face means this is column, the right side is the heavily loaded area. By checking the right side column face bending moment, column face means this area. If we check this area, this section, then that section is the maximum critical section. That is enough for finding all that. Moment at the face due to upward soil pressure caused by load only. Breadth and length face, total length from column face to this distance from column face to end, that is means L face, toe side, into Q load. This is a constant load, Q load into that distance by 2. The total distance by 2 means L face by 2. This L face by 2. Applying this value is coming like this. Moment at face of the column due to upward soil reaction caused by column moment. Column moment. This is this formula. This is breadth into length, the same thing. Q at the face of the column, average into distance 2 by 3. On calculating the bending moment caused by the column moment is this one. Adding these two, this is the total moment caused by the upward reaction of the earth, and this is 421 kilonewton meter. For checking these things, moment carrying capacity of the full section is 0.14 into FCK BD square. This is a normal formula used in IS 456. This bending moment capacity is 1252, so this is well above the available moment, so no problem. So we can calculate the reinforcement. M by BD square is required for using that tabulation in IS 456 design aids. This value is this much. As per design IS 456 table 2, yeah, this is table 2 IS 456 design aids. For M by BD square value is 0.94. This is M by BD square. 0.94. Take it as 0.95 also. For the steel, percentage of reinforcement is, yes, this value is 0.232. This value is 0.232. There is a value. By applying this thing, the values are already getting changed. So by using this is the normal table. The square cross-sectional area of 10 mm rod, cross-section of 12 mm, cross-section of 16 mm rod, these means area of reinforcement, percentage of reinforcement into this area. The area of footing into percentage of reinforcement is this much square meter. This is into square mm. Required steel cross-sectional area for, this is 12 mm. Is number of rods is 14.72. So this total mm spacing is 78.12 is the spacing of 12 mm rod in the breadth side. So bending moment, the same thing we have arrived in the longer side. 12 mm rod at 78.12 mm spacing. Bending moment and arriving the tensile steel in breadth side. Thus we are breadth side we are calculating. Similarly, on the same type of formulas, we are arriving this as 12 mm rod at a spacing of 106 mm. So this is result. The result is given in this box. Rods in the length side, 12 mm diameter rod at 78 mm spacing. Rods on the breadth side, 12 mm diameter rod at 106 mm spacing. Length of the footing is 3.81 meter. Breadth of the footing is 1.15 meter. Column center is to be placed at 1.24 meter distance from the heel side. That I have deducted that eccentricity from the one side length. That the balance is this much. The column center to be placed at the middle as far as the breadth side is concerned. Depth of the footing is 0.67. This is the result, and this may be recommended to the builder for executing that column with the moment and load which we saw in the beginning. Okay, thank you for listening so much. See the design once again. You will feel it very easy, and this method is very accurate. And the textbooks are defining the same thing using some formulas. Instead of using the formula, this method is the basic method. From the basic principle we have arrived at. This is more good. People who like this, please give a like to me and subscribe my channel. Share this. Thank you.